All right, thanks everybody. So today we've got visiting us from Hawaii, where he works with Ben Chappie and others in the Assassin group, right? Mm-hmm. On tidal disruption events. He's going to be telling us about messy eaters. So I encourage you to meet with him later today if you haven't already. He's trying to make the most of his time in the Midwest. This is a long flight from Hawaii. So looking forward to your talk, and thank you.
Great. Thank you so much, Decker, for that introduction. Yeah, I'm very happy to be here to talk about various types of accretion onto supermassive black holes, and in particular, the detailed insight that nuclear transients and following them up allows us to get into this type of behavior. So for some broader context on supermassive black holes, where better to start than the center of our own Milky Way? And so on the right, I'm showing some work from the Keck UCLA Galactic Center Group, which took images in the infrared over many, many years, mapping out the orbits of stars around this central unseen massive companion, which is, of course, the central supermassive black hole in our galaxy, Sagittarius A star. And while this type of work is excellent and gives us great constraints on the fact that there is a black hole and its mass, it's obviously very expensive and doesn't work for any other black hole out there. But it is well known now that all massive galaxies like our Milky Way harbor a supermassive black hole in their center. And indeed, it seems like the galaxies in which these black holes live seem to care about the black holes. So on the right, I'm showing the well-known M-sigma correlation between the mass of the central object and the velocity dispersion of stars in the bulge is a proxy for the stellar mass. There's also similar correlations between supermassive black hole and total stellar mass in the galaxy, V-band luminosity, things like that. And this type of correlation indicates some sort of coevolution between the black hole and its host galaxy, possibly even the fact that there's some sort of link between the two, maybe some sort of feedback processes from the black hole that moderate the star formation in the galaxy and vice versa. And this all seems to tell us that if we want to understand how galaxies grow, we also need to understand how supermassive black holes grow. And there's been quite a bunch of work done on this, in particular using the luminosity functions of active galactic nuclei, so these are actively accreting black holes, and trying to invert that and essentially integrate in redshift and understand how did the masses of supermassive black holes grow over time. And this type of work tells us two key things. One, that it is in these phases of active accretion that most of the black hole mass is accumulated. Mergers are a relatively small fraction of the total mass. And that there's this cosmic downsizing effect, where these massive black holes grow most of their mass early in the universe, but lower mass supermassive black holes, indeed the ones kind of like Sagittarius A star, are growing a significant amount of mass relatively late in the universe. And as you start to get to the lowest end of the supermassive black hole spectrum, they're perhaps even actively accreting today. And so if we want to broadly understand black holes, we need to do a bit of a scaffolding approach. To kind of form the roots or the foundation of our understanding, we can, of course, go out and, after many, many years of technological advances with the EHT collaboration, go and take an image of a black hole. And this, of course, gives us excellent constraints on the mass, tells us that we understand how black holes work, that our theories of general relativity are quite good. But again, this is really only possible for two objects, M87 and Sagittarius A star. We can expand that out in terms of good constraints on masses and the properties of black holes to a few tens to about 100 nearby galaxies. We're using either space-based telescopes or large aperture ground-based telescopes. We can resolve the orbits of stars or gas in the sphere of influence of the black hole and get measurements that way. But again, this is somewhat limited towards nearby galaxies. And so we need something else that allows us to study many, many black holes. And the first of those is these active galactic nuclei, or AGNs, which of course, due to their high energy emission, are relatively easy to select from quiescent black holes that are not accreting. But we do also want a way to study these otherwise quiescent black holes, which are about 90% of all black holes in the nearby universe. And so we need something like transient events. For instance, this is an example of a tidal disruption event when a star gets ripped apart by a black hole, and these give us insight into these otherwise quiescent black holes. And so throughout my talk, I'm going to focus on things in this red box up here, these AGNs and tidal disruption events and other types of transients that are really, one, a great way for us to study a large number of black holes, but also where the active mass growth for these supermassive black holes is actually occurring. And so throughout the talk, I'd like to kind of have two main threads running through. One is the physical origin of this material that eventually accretes onto the black hole, whether that's gas in an AGN disk, things that can get disrupted by the central black hole, like clouds or stars, or even interesting things that we can learn from stars on bound orbits that punch through a disk and give us some interesting constraints. But in addition to this physical picture, I'd like to also have us keep in mind this kind of parameter space of accretion onto black holes, where one axis that I'd like to focus on is the supermassive black hole mass, which of course is the key driver of essentially all physical and time scales in this system. Of course, you can see that AGNs and different types of transients occur over a wide range of supermassive black hole masses, but also the Eddington ratio, where the Eddington ratio is the ratio of the luminosity we see to the Eddington luminosity, which is essentially the maximum luminosity. It's where you take the gravity that's pulling the material onto the black hole and the force from radiation pressure pushing out. And when those are balanced, you're at an Eddington ratio of 0. And the Eddington ratio is also an interesting probe of the type of accretion flow you see. So at the very low end, we have a radiatively inefficient accretion flow, where much of the mass just feeds onto the black hole and doesn't come out in some form of luminosity. And this kind of percent to tens of percent range, it's much more of the kind of typical accretion, the thin disk that you might be familiar with, that's much more radiatively efficient. And then the super Eddington accretion, where you have perhaps a thick disk and you're also quite efficient. And so as you can see here, various different types of AGN behaviors, various different types of transients also span a range of this Eddington ratio, allowing us to study different types of accretion onto black holes. And so I'll return to this throughout the talk to kind of highlight the different regions of this parameter space that I'll be discussing. And so first, I'd like to talk about gas accretion. So this is the AGN phase of supermassive black hole growth. And these in the local universe, depending on how you want to count AGNs, are about 5 to 10% of all galaxies host an AGN. They're relatively easy to select because their high energy emission gives rise to interesting things like narrow line ratios that are not consistent with coming from ionization from stars, compact X-ray emission, different colors in the mid-infrared, optical, other bands that are distinct from stars. So they're relatively easy to pick out in general. And in terms of this parameter space, they can occur on any mass black hole, although, of course, the observables that you would see are a little bit different depending on the mass. And they have a range of accretion rates or Eddington ratios. The kind of normal AGNs sit up here anywhere from 1% to tens of percent, even about Eddington, or sometimes slightly higher. You have low luminosity AGNs, which are these radiatively inefficient ones, down at the bottom and extending even below. And then this kind of fuzzy band of changing look AGNs that seems to blur the line here. And I'll return to this more throughout. And so for AGNs, after many years of study, starting with the first identification of AGNs and quasars and trying to put together this physical picture of the wide observational zoo of AGNs, we've come to the unification model, which posits that the observable properties of AGNs are the result of a few different physical parameters, and changing those changes what we see. The first separation is between radio-loud and radio-quiet AGNs, where essentially this is related to whether or not you are able to launch a jet. So this is mostly the magnetic field configuration and the spin of the black hole. Although I'm not going to focus too much on these because these are only about 10% of AGNs, and it's a bit more tricky to connect their physics all the way down to accretion. So I'll focus mainly on the radio-quiet AGNs, which are the rest, the 90%, where the viewing angle is the key physical parameter here, effectively the viewing angle relative to the torus here, this dusty torus. And the main separation is between these Seifert-1 or broadline AGNs, where our view to this central region is unobscured, and so we can see the blue and UV emission from the accretion disk. We can see the broad lines from the broadline region. So an example shown up here. For a Seifert-2, we are blocked by the torus, and so we no longer see any of those inner regions. We're only seeing the narrow line regions farther out that still see the ionizing radiation from the AGN, but we're no longer able to see any of that blue continuum emission or the broad lines. And so this is a great physical picture in general. It describes a lot of what's going on in AGNs, but it's already clear that there's some problems, and that's one of them is the fact that we have AGNs that seem to change their type from broadline to narrowline or narrowline to broadline. And so one example on the right here is the well-known source Markarian 590, which is an example of a turn-off AGN. And effectively here what we're seeing is in the 80s and 90s, we have this very, very strong, broad H-beta that eventually goes away by the time of publication for this paper in 2014. It's effectively gone, and it's entirely narrow. But we don't only see examples of turn-off AGNs, we also see turn-on AGNs. So here's an example, NGC 2617, where if you look from a few decades ago, it looks in the continuum largely like a normal galaxy and with only narrow lines, particularly for H beta here. But in 2013, it had somewhat of a flare that was accompanied by this strong blue and UV continuum, as well as many broad lines of hydrogen, turning it effectively into a normal Seyfert-1 galaxy. And so the interesting thing about these changing look or changing state AGNs is this change can't simply be due to a viewing angle because the timescales are much faster than you could change, our viewing angle towards the torus. And so there must be something else going on. We also see, now that we have many surveys that have been surveying the sky on a roughly daily cadence for many years, these example of flares known as rapid turn-on AGNs. And so these had these rapid brightening and smooth flares in general, but the interesting thing here is that they're also accompanied by rapid spectral changes. So for this example of Assassin 18AL, you'll see that early on you have very narrow H-beta, this is H-alpha, very narrow H-alpha early in the flare, but by only a few months later, this strong, broad H-alpha profile is grown. And so I don't want to go into much of the details now, although I'm happy to answer questions or discuss later. But there's quite a slew of different physical interpretations. Some of these are intrinsic to the disk. Some of them require other things like maybe a transient or obscuration to explain these changes. So there's quite a lot of parameter space there in terms of understanding what's going on. But it's not only these rapid changes that we see in AGNs, we also see these slower timescale changing look events. And this is really where the optical surveys have been critical in terms of understanding how these change over what timescales. Yes?
For models like magnetic inversion changes in the disk, are there any spec pole measurements of any of these objects?
I don't know about after the flare, although interestingly, the object or the AGN where this object happened is a particularly strange object. It's one of the true Seyfert-2s, so it doesn't seem to have this broad line. It's not particularly clear if that's connected to this event, but yeah, that would be an interesting thing to study, go back after the change. But returning to these longer timescale events, sometimes we see AGNs that do particularly strange things that are outside of the normal realm of AGN variability. One example here is NGC 5273, which has this kind of interesting brightening that's clearly not just the typical variability that we're seeing. And indeed, when we took a spectrum, I've connected the purple and the green here, I'll come back to the green in a second, we saw that as compared to these older SDSS and Palomar spectra, that the H-beta profile had changed considerably. It was now very consistent with a Seyfert-1-like broadline state, and so that this is an example of a changing look AGN. But it also seems that perhaps we've seen multiple changing look events in this particular source. The green highlighted region here is a flare that occurred actually during a reverberation mapping campaign done by Misty Bentz. And when you look at the spectra here, again, it looks effectively like a typical Seyfert-1 with these broad lines. And so while we don't have the coverage to know for sure, it seems possible that during quiescence, this source is more of a Seyfert 1.5, has relatively narrow H-beta, somewhat broader H-alpha. But when it goes above some critical Eddington ratio or critical flux level in here, it changes to a more typical Seyfert-1. And so perhaps we're seeing that there is some ratio that can set what the broad lines look like in these AGNs. And so I've been interested in also looking at these not only in the optical, where much of the work has been done so far, but also in the near infrared. And so again, I'm showing here NGC 5273. This is an archival spectrum taken with specs on IRTF. And you can see that there's effectively no broad lines for any of the normal species of helium, hydrogen, oxygen. But during this recent flare, we took several near-infrared spectra and found that the picture had changed quite considerably. You now do have all of these broad passion lines, some of these helium species. And this is interesting, right, because we would potentially expect that if it's an obscuration change, that maybe the optical would change, but not so much the near-infrared. We also see examples of turn-off AGNs. So here's an example of the well-known Seyfert Markarian 926. Again, showing some archival spectra here that show the very broad lines and blue continuum that you would expect for this type of AGN. And I recently found this object by looking in assassin data. Effectively, the source had decreased in flux and its variability amplitude had shrunk. And when we followed it up in the infrared, we found that the spectrum had changed again, losing all of these broad lines of Paschen alpha, these Paschen gamma helium lines, and we no longer see this very strong blue continuum. So again, I think this is a pretty strong evidence that many of these changing looks are not due to obscuration, effectively because out in the K band, this is about a factor of 10 less obscured than the V band would be. And this also seems to support this kind of critical Eddington ratio, where both of these sources, and indeed many others, seem to have this change occurring around an Eddington ratio of 1% or so. It's not particularly clear what that would mean, although this is also the place where you have a change from this more typical classical radiatively efficient disk down to these more radiatively inefficient accretion flows. And perhaps this is coupled to how the broad lines are formed and all of these different things. And so returning to the unification model, yes?
Hi, sir. The obscuration you refer here is only the dust or including both gas and dust?
For the infrared and the optical, it's mostly the dust that matters. And so, right, the thing here is, assuming Milky Way-like dust, we have these ratios. But for typical dust properties, the the redder ends of the near infrared should be less extincted than the optical. And so
this cannot rule out the obscuration change from batch?
Yeah, in general, that's true. But, taking a typical gas to dust ratio for most of, the ISM, that's probably relatively similar in AGNs. I think that you would expect to see changes. One thing I should note is that, I don't have the X-rays here, but the X-rays would give you a good handle on the gas obscuration in particular, much more so than the dust. So taking a bit of a step out from the gas in a disk from an AGN, we can also have transients resulting from the disruption of other sources in the galactic centers, perhaps even molecular clouds. And so in terms of what these might look like, it's a bit unclear. There isn't much theoretical or observational work, so I think we'll just leave it kind of as a question mark right now. But there is some good reason to believe that we might actually see these events. Again, returning to the galactic center, in the infrared, we see a lot of sources close to the black hole. The ones that are labeled here are examples of molecular clouds. And looking at the source X7 in particular over several years, starting from the top left to the bottom right in time, we see some evolution for this molecular cloud, both orbital motion, but also some tidal stretching towards the black hole. And so this seems to suggest that at some point in time, perhaps this source will be close enough and stretched enough that some of the mass will be able to accrete onto the black hole, perhaps powering a transient. And indeed, there's one source in the literature for this, for which this is potentially an explanation. This is this source up here, AT 2021 LWX. Which has a very high peak luminosity of nearly -26 in absolute magnitude, corresponding to about a solar mass per year of accretion. And when we look at comparing to many other transients, this is clearly both much longer lived and much, much more luminous. So it's very likely not a supernova. It has to be some sort of accretion. So when we look at the spectrum, it suggests that perhaps it's not a normal AGN, right? We don't see many of the typical lines that you would expect to see for an AGN. And even so, this very smooth behavior is not typical of AGNs. And so in the literature, there's two papers that have looked at this object, and they have two differing explanations. One is perhaps you're seeing the tidal disruption of a very massive star, in this case 14 solar masses, or you're seeing the tidal disruption of a molecular cloud. And I think the main issue for this 14 solar mass star is that when you look at the photometry of this host galaxy, there isn't any strong evidence for active star formation. And so it's already a bit of an issue, how do you form such a massive star without active star formation? But even if you could get around that with something like a top-heavy IMF in the center of the galaxy or something else, you then run into an issue of how do you actually kick a star onto an orbit that gets it disrupted in only the few mega-year lifetime of such a star. And so I think that's perhaps some evidence suggesting that a tidal disruption of a molecular cloud is a little bit easier because you don't have any of these requirements. It simply has to get close enough that some of the mass is stripped off. But clearly, this is still speculative. I think we have more work to do in terms of trying to understand these. But I will note that one interesting thing is that this redshift of about 1 for this source would seem to imply that the rates of these events are probably pretty low and that we need to probe a very large volume to find more of them. If we have a disk around the black hole, whether that's from an AGN, something more quasi-static like that, or the disruption of either a star or a cloud, and there's a bound star orbiting around this black hole, we can get transients from the interaction of the star with the disk as it passes through on its orbit. And returning to this type of diagram, I think it's really, we only need a disk in the first place, so I think that could happen nearly anywhere here. You just need to have a star that's orbiting. And so we do see these in nature, particularly these have been seen in the X-ray for several years now as quasi-periodic eruptions. Effectively, we're looking at these sources that have, as the name implies, these periodic eruptions. They flare, they change their spectral state a little bit. And they've now been found, both using things like Rosita and Swift and other missions, having quite a range of timescales, which is interesting because one of the things that's potentially very powerful for these types of events is that because they're stars interacting with the disk, if we can understand that interaction very well, we can potentially get a good constraint on the surface density of the gas in that part of the disk, which is otherwise very difficult to do. And as the orbits are, in general, very close to the black holes, they'll be subject to GR effects and precess. And so we can not only get potentially an independent constraint on the mass from that, but we can also trace out different parts of the disk and perhaps get a gas surface density profile for some of these objects. But it's not only in the X-ray that we see these events. We have one example so far of an optical QPE, which is the well-studied source Assassin 14KO, found by Anna Payne, who just recently graduated from the group I'm in Hawaii. And this is a repeating nuclear transient in a known AGN. As you can see here, we've seen many different flares. This is just 6 of them observed from the optical on the bottom in the V band up to the UV. These are all from Swift. And when we phase fold these different flares in time, we find that there's excellent agreement from flare to flare in the UV optical, both in the time scale of the flare, but also the flare shape. They have consistent rises and declines in general, although there's some small changes, especially as we've looked at more and more, we see some variability. And we also see some interesting different, but also relatively consistent behavior in the X-ray where there's a dip that occurs at the UV rise. And so the original interpretation in our papers was of that of a partial TDE where you have an evolved star, so a bit puffier than something like the sun that's orbiting, and as it approaches its pericenter, it gets close to the tidal radius, and some of that mass is stripped off and accretes onto the black hole every 115 days in this case. But there's some other interesting evidence for this flare, and that's that there's some orbital evolution. It's not strictly periodic. There is a bit of a negative period derivative, meaning that every flare is occurring slightly closer together. And so the idea for the tidal disruption case is that perhaps this is tidal heating. We're losing some of the orbital energy to the heating. But it's also potentially consistent with this type of star disk case where rather than an evolved star, you perhaps have a more solar-like star that punches through the disk, and you have hydrodynamic drag that powers, or that's able to give you this type of orbital decay. And so these are both interesting scenarios. It's not particularly clear yet what the correct answer is. And with only one of these objects, we still have quite a bit of parameter space in terms of these repeating optical flares and AGNs to understand what's going on. And so finally, I've talked a lot about different types of behaviors onto black holes. I've mentioned TDEs a few times, but now I'd like to dig into them in a bit more detail. And this is what results from when a star that's otherwise happily living its life in the center of a galaxy has a gravitational interaction with another star and gets kicked onto an orbit that passes it very close to the black hole, and it gets ripped apart. And so about half of this material remains bound and eventually accretes back onto the black hole, but the other half leaves the system, likely in the form of some form of outflow. And so first I'll talk about the most commonly studied and perhaps best understood type of tidal disruption events, the main sequence tidal disruption events. And these occur around relatively moderately massed supermassive black holes. This upper end is a bit fuzzy, but this is effectively related to where, for a given supermassive black hole mass and spin, the tidal radius goes within the event horizon. And so you simply wouldn't see the transient that results from such a tidal disruption. And they're generally about Eddington or super Eddington accretors. And so returning to that point here, a lot of the early theory that disrupted stars and looked at the fallback rate found two key things about the behavior of these TDEs. One, that they had highly super Eddington mass return rates near peak, although I should note that super Eddington mass return doesn't necessarily lead to super Eddington luminosity, and that they have this characteristic power law decline in time, often t to the minus 5/3, which is sometimes used in the literature to select something as being due to a tidal disruption, perhaps, separate from something like an AGN flare or supernova or something else in the center of a galaxy. And so when we look at observed examples of TDEs, this picture is generally pretty good. For the well-studied event Assassin 18BG here, we find that near peak it's pretty close to Eddington luminosity, so that's fully consistent with this super Eddington mass return. And in general, these power laws do describe the late time decay quite well. If we go back to some of the early theory on the SED, effectively taking this Eddington radiating event and the tidal radius as the characteristic physical scale for these events, this would give you a temperature that peaks at around a few times 10 to the 5 Kelvin, peaking in either the very extreme ultraviolet or the soft X-ray. But when we return to the observed examples of TDEs, we find that many TDEs don't look like this. For example, a lot of the TDEs that we've studied so far have been selected in the in the optical and are UV dominated rather than X-ray dominated. And indeed, with missions like eROSITA combined with things like these optical surveys, we find that the rates of these optically selected TDEs are somewhat higher than the rates of X-ray selected TDEs. And so this is a bit of a surprise, but it's given us the opportunity to study them in great detail, and we found a few interesting trends. So here is just a little bit of an outdated example of some TDE black body parameters. I don't want to go into any of the details on individual events, but just want to highlight a few key trends, which is that there seems to be this relationship between the peak luminosity and decline rate of a TDE. In particular, these most luminous TDEs seem to decay much more slowly after their peak as compared to these less luminous TDEs that fall off relatively quickly. In terms of their black body radii, the evolution generally follows roughly the luminosity evolution, but their scale is quite a bit larger. Instead of being close to the tidal radius, they're factors of 10 or more than the tidal radius that you would expect. And then perhaps most interestingly, the black body temperatures are both about an order of magnitude cooler, but also, very interestingly for accretion-powered flares, they're quite constant throughout their evolution, which is a bit of a surprise. And so this has led to some key questions for TDEs, which in principle is, where does this UV optical emission actually come from? And there are two key models so far. One is that as you disrupt the star, these disrupted tidal streams eventually precess and flatten and interact with each other at these shock points, and this could perhaps power the emission that we see. The other model posits that you very rapidly circularize this material and form a disk, and that unbound material from the initial encounter that forms this outflow serves as a layer for reprocessing this harder emission in the X-ray into the UV and optical that we see. But unfortunately, due to somewhat similar predictions on the energies and a lack of key kind of observational things that we can hang our hat on and say this is one model or the other, it's still a bit unclear which of these models is most likely to be true. But I think fortunately, after studying TDEs for about 10 years now as a community, we have some interesting trends that are giving us some insight. One of these is this peak luminosity decline rate, which I've talked about a little bit before. Again, the physical interpretation is a bit unclear as to what this means and if this points towards one model or the other. But I think actually perhaps we're starting to see, with following even more events, and in particular finding these fainter and faster events, that maybe it's not a single relationship at all. Maybe we're starting to see different TDE subtypes, somewhat akin to different types of supernovae, although of course the physics is quite different. But perhaps we're seeing this kind of normal class of luminous TDEs that sits in this cloud up here, and that we have these fast and faint TDEs that are lower in luminosity and evolve much more quickly. And I should also mention that there are even more exotic examples, some fast and slow TDEs, different things that we're only now, after surveying for many years and covering the sky in great detail, becoming sensitive to. And so perhaps one of these hopes is if we can fill out this parameter space in more detail and really understand, the different groupings that might exist here, that they may connect back in some way to these different models. We also get some interesting hints from looking at the X-rays for these optically selected TDEs. It's only for about a third to half of the optically selected sources that show any sort of strong X-ray emission. But interestingly, even for those sources, which are shown on the right here from a recent ZTF sample paper, they're all optically dominated throughout their evolution. Even sources that show strong evolution in this type of ratio are effectively always at least at a 1-to-1 level between their X-ray and UV optical emission. And so I don't exactly know what this is telling us, but I think it's something interesting in terms of what's actually powering this emission. And so in addition, I think this is where a lot of our best information is coming from, is these different spectroscopic classes of TDEs. So now that we've studied TDEs in great detail, especially getting good coverage for their spectra, there's 4 key classes that have arisen in the literature. That's the TDEs that show both hydrogen and helium emission, TDEs that only show hydrogen emission, TDEs that only show helium emission, and then finally this recent class of featureless TDEs that seems to show no strong emission lines but has this very blue continuum. And so through many different types of work, whether that's fitting their UV optical SCDs as black bodies, using some models, looking at their spectra in great detail as a function of time, we found some interesting trends between these classes. In particular, the sources that show this helium-2 emission, so the hydrogen plus helium and helium, seem to have smaller black body radii, smaller full-width half maxes, and impact parameters that are consistent with deeper tidal encounters. So these are potentially all suggesting that the sources that show helium might rapidly form disks, and so rapid circularization and form a disk, which would perhaps make sense for why you're seeing this helium-2 emission, which requires emission above 54 eV to be produced. The opposite is true of events that only show this hydrogen emission. They have larger black body radii or larger full-width half maxes and weaker encounters, and so perhaps this is the other scenario where you're seeing the shocks and driving outflows, and you're only seeing the outflowing material get ionized by this shock. And that lower energy and hydrogen-rich material that's flowing out is driving the fact that we're mostly seeing hydrogen in their spectra. And so I, again, should note that this is a bit speculative, and we're still looking in great detail at this, but perhaps we're starting to see that the spectroscopic classes might give us a good mapping between observables and different physical scenarios. And so returning to this, I think we're, perhaps starting to see that both of these models may power TDEs. Perhaps even within the same tidal disruption event, you can have a change where you might have shocks dominating the emission early, and once you form a disk, you can perhaps have X-ray emission and see something like this. But regardless of what the true physical, regardless of the difficulties that we've had in doing this, I think it's very important for us to understand the physics, not only to understand TDEs themselves as interesting objects, but also because TDEs are great probes of quiescent black holes, as I mentioned at the beginning. In particular, they're probably our best probe of these very low-mass supermassive black holes, extending even into the intermediate mass black hole regime. But of course, to actually use the TDEs to give you any sort of meaningful constraint on mass and spin for black holes, we need to understand the physics of the TDE. Otherwise, it's just too difficult to untangle all of that different observed emission. And so this is, again, just to return to this is some nice recent work by ZTF looking at the TDE mass function. And we see that if this trend continues, again, TDEs are probably our best way of perhaps even identifying intermediate mass black holes and then moving on to even get some constraints on the physics. In addition to main sequence TDEs, you can also tidally disrupt white dwarfs. And so these occur on even lower mass black holes than what I've talked about so far, kind of less than 10 to the 6 solar masses and even down into the intermediate mass regime. And so there's various different models for what these might look like, but in particular I'd like to focus on this example of what's called a 1A TDE, where effectively you have a white dwarf that has a very deep tidal encounter with a black hole, so deep, in fact, that as you tidally stretch the star in one direction, you compress it in the other and trigger nuclear burning. And so this gives you a transient that's somewhat similar to a type 1A supernova, but generally less luminous because there's effectively no mass limit for this disruption, and so you can have much less nickel mass that eventually powers this transient. And so these are very interesting, of course, as probes of these low-mass black holes and the white dwarf TDs in general. And through looking at ZTF data and follow-up spectroscopy, there's a few plausible candidates out there in the literature. And so I think we're starting to really potentially build a sample of white dwarf TDs and extend our knowledge of tidal disruption events outside of kind of the solar-like stars, main sequence stars. And so I've talked quite a bit about what we know so far, the current state of affairs in studying nuclear transients, but I'd like to take some time at the end to go into a little bit of where I think the field is going and some future opportunities for research. The first is something that's very close to my heart, these sources that we've nicknamed ambiguous nuclear transients, or ANTs, which seem to be this kind of in-between point between AGN flares and tidal disruption events. They seem to show some observables consistent with both classes. Starting in the UV optical, we see that they're generally very well fit by black bodies, which is much more consistent with the tidal disruption event than an AGN flare. But unlike TDEs, they nearly all show strong X-ray emission, and in particular, this X-ray emission is much more power law-like than a black body, like a very soft emission that's consistent with TDEs. And so I think what this is probably most likely to be is some sort of transient in an AGN host, perhaps even most likely a tidal disruption event in an AGN where the interaction between the tidal streams and the disk give you very different observables than you would otherwise see in just an AGN flare or just a tidal disruption event. And again, even though it's a little bit unclear what they might be and what this means for understanding, I think they give us a good constraint into this accretion physics and disk physics. But we're also finding a decent number of them. Sky surveys have found, depending on how you want to count these ANTs, a few tens of events. And this puts the observational rate at about 10% of the TDE rate, which again is, I think, another piece of evidence suggesting that perhaps these are TDEs in AGNs. And so recently I did some work looking at the infrared light curves of these events from WISE, in particular trying to understand what is the distribution of dust around these black holes. And what I found is that nearly all ANTs show a very strong dust echo in the infrared. And when I computed the covering fraction by taking the peak luminosity in the infrared and comparing that to the peak UV optical luminosity of the flare, I found that the ratios were much higher than you see for TDEs, which are kind of about 1% or so, consistent with relatively dust-free host galaxies. But the ANTs live up here at a few tens of percent in general, and extrapolating this trend for other AGNs, well-studied AGNs, we see that there's this very nice qualitative agreement, which is one, a good independent check that these are AGN-like, or AGN host galaxies or AGN-like geometries near the black hole. But I think this also gives us some interesting analogies to the recent push for infrared-selected flares and infrared transients. And so some examples of those are these relatively agnostically selected mid-infrared outbursts, so it's effectively looking at WISE emission and finding very large flares. So here you see that in general these objects are relatively quiet prior to their flare, and they have these very large, often smooth flares, but sometimes with some stochastic variability. And we also see examples of perhaps dust-obscured TDEs, where you see these smooth flares that have, again, this power law-like decay that's consistent with the TDE, but they're only seen in the infrared. When you look in the optical, for this example, in Assassin data, there's no optical counterpart, so they're very highly obscured. And so the interesting thing, and where I think ANTs fit into this kind of picture, is that while they look much like these infrared flares in their infrared light curves, they do have this multi-wavelength emission, this X-ray, this UV optical. And so perhaps we can use them at least statistically as a way to understand the multi-wavelength emission for these events that are otherwise too obscured for us to see their full emission. In terms of looking for more cloud disruptions, I don't know what the best way to look, given some of the uncertainties in theory, but I have found by looking at sources in my thesis, these this class of kind of long-lived, very luminous flares. I'm showing one example here that was detected by the Gaia mission, showing the Gaia and Atlas optical light curves and some WISE infrared data. And we see that these are very luminous, very long-lived flares, not consistent with any other types of transients I've talked about so far. Again, much more luminous. And this is smoother than a typical AGN flare that you might expect. But interestingly, they do have spectra that look pretty consistent with AGNs. You have these broad lines of magnesium and neon, maybe even this iron 2 complex here. But of course, then the question is, why are we seeing emission that's consistent with a black body? Why are we seeing these smooth flares? So I think that I'm not saying convincingly that this is an example of a cloud being disrupted, but perhaps this is one of the ways for us to find more of these. And even if not, it's an example of a very rare type of AGN behavior that we don't see very often. So I think there's interesting things to look for these long duration flares in general. In terms of star-disk interactions, I think there's potentially a lot of interest in looking for more sources like Assassin 14KO. So Assassin 14KO, as the name would imply, was selected using Assassin data, but now we have other surveys, in particular Atlas, which is also now all sky, and goes about a magnitude deeper than Assassin. So I think there's quite a bit of promise for looking for more of these types of events and deeper and larger surveys and expanding our understanding of these types of events to different types of black holes or different masses of black holes, different timescales. So I think there's quite a bit to be done in finding more 14KO-like events and expanding and building this sample of optical quasi-periodic eruptions. And finally, in terms of the future of tidal disruption events, I think one of the interesting things is this class of coronal line emitters, which show these very high ionization lines of things like iron, or species like iron, sulfur, argon, etc. And they're called coronal lines because a lot of these lines are the same lines that we see in the solar corona. And the fact that these lines have very high ionization potentials, tens of eV up to more than 100 electron volts in some cases, gives us interesting probes into the extreme ultraviolet emission that's otherwise unobservable because it's so readily obscured by dust, whether that's in the host galaxy or in our own Milky Way. And through many different studies, both some earlier on looking at the time variability of these coronal line emitters, as well as some recent work that I did looking at the host galaxy properties, these events seem very convincingly linked to TDEs. And so we can possibly use these coronal lines to not only study the luminosities of the EUV emission, but also potentially use the ratios of lines with different ionization potentials to give us a handle on the spectral slope and the SED and the EUV. And this is very important because related to the different models, there are different predictions on where a lot of the energy from TDUs should be coming out, and perhaps even a factor of 10 or so more emission than we're seeing in our UV optical probes. It might be coming out in the EUV, and we need some handle on that emission, which of course is not looking at the EUV directly, so we need something like the coronal lines to let us probe that. And finally, I've mentioned main sequence stars, I mentioned white dwarfs, but you can also have the tidal disruption of an evolved star, although here these happen around more massive black holes because the stars have larger radii and can get disrupted farther out, and generally lower Eddington rates. And so some nice work has been done on the mass return rate for these objects, here showing main sequence TDEs again, but as you get to various different types of evolved stars, they have generally slower timescales, longer timescales. Instead of the few months of a normal tidal disruption, you go up to perhaps many years, and lower accretion rates. But now that we have surveys like Assassin, Atlas, CTF, Pan-STARRS that have been surveying for many years, we're starting to get sensitive to these types of events and potentially can select them or at least get good constraints on their rates. But there is a bit of a problem, which is that we don't have any examples. And I've looked a bit so far, and it's been difficult. And I think that's due to two main things. One is that we really have very little idea what they should look like. We have good constraints on what their mass return is, but going from mass return to observables is not particularly easy. And in particular for TDEs, there's quite a wide dynamic range and difficulty in terms of taking hydrodynamic simulations and running that through radiative transfer models to get to observables. And another thing is that as you get to many of these different types of evolved star TDEs, you start to get these Eddington ratios that are more similar to AGNs than TDEs. And so there is a bit of a question, at least in my mind, of, would you expect it eventually, after accreting at, a percent of Eddington for tens of years, to look more like an AGN than you would otherwise expect? It's definitely not as simple as taking the TDE observables and scaling them down in luminosity and stretching them out in time. And then the other one, as I just mentioned, AGNs, is that AGNs also vary on longer time scales, and perhaps there's some difficulty in actually selecting these kinds of very low amplitude, very long-lived transients from AGN activity in particular. But despite this, I think there is a very strong rationale for studying these, and particularly these are the only viable probes of these massive quiescent black holes, which are, of course, the relics of high redshift quasars and other things like that. And so I think we have a lot of work to do, but potentially some very interesting things to come out of studying these evolved star TDEs. And so I've talked about a lot of different transients and all these things occurring in the center of a galaxy near the black hole that all occur in this little red box, which I should note is already massively, massively oversized as compared to this galaxy. But if we think that things like the M sigma correlation and other similar correlations tell us that there is some link between galaxies and black holes, we need to understand them both. Right? All the things that happen in the black holes could potentially have implications through feedback to the galaxy and the star formation processes there. And the gas that eventually moves down towards the black hole and forms the stars that get tidally disrupted, or the gas that eventually feeds it as an AGN, come from the outer parts of the galaxy and feed through. And so there is, we need to keep both of these in mind. We need to be able to understand both together if we really want to understand how galaxies and their supermassive black holes evolve. And then finally, I'll leave you with my summary and say that, I hope I convinced you that transients, whether that's more typical AGN behavior or these flares from TDEs, are interesting ways to study black holes. In particular now, I think we're in an excellent time with all-sky photometric surveys, things like spectroscopic surveys, and a wide fleet of recently launched and soon to launch space missions that give us very nice constraints on these different types of accretion behaviors. In addition to a lot of what I've talked about, black holes and their flares are also excellent probes of a wide range of physics beyond what I've mentioned. And so I think there's quite an interesting, quite a strong reason, and they're very interesting to study these transients for many different reasons. And so with that, I'm happy to take any questions.
Thanks for the talk. Can you elaborate more on how to distinguish between a rapid turn-on AGN and a tidal disruption event?
That's an excellent question. So indeed, one of the models for these rapid turn-on events is perhaps you are seeing a tidal disruption event in an AGN. So looking at this source in particular, Assassin 18EL, there are some people and some groups that have suggested we are seeing a TDE. I think there's also evidence that perhaps it is something like a magnetic inversion. But you bring up a good point, which is that it is difficult. Some of the things that you try to do, where you take typical AGN-like behavior, right? So luminosity-dependent temperature evolution, variability, and you compare to things that you would expect for a TDE, right? The different types of X-ray emission, the black body temperatures, and you try to look that way. But I think one of the issues is, if you have an AGN disk and you drop a star in there and get it tidally disrupted, it's not particularly clear what you might expect to see. There's been work on the mass return, the hydrodynamic side, but as I mentioned, I think one of the consistent themes in this field is taking that through radiative transfer and understanding observables. So I don't have a particularly good answer, but you've hit on a key question: is how do you select TDEs from other AGN behaviors?
Thank you.
Thank you for the talk. You had mentioned a link between coronal line emitters and TDEs, and in particular a link with their host galaxies, and I was wondering if you could elaborate on that.
Yeah, so some of the work that's been done to link them is basically looking at these coronal lines over time. So the ones up at the top here were selected in SDSS spectroscopically, basically as sources that were not obvious AGNs, but had these very high ionization lines. And many of them have their coronal lines change over time, which implies some sort of transient event. I don't have any plots right now. I'm happy to talk later, but I've looked at the host galaxies in terms of their stellar mass and star formation rate, and they seem more or less consistent with TDEs. There's slightly higher star formation, which makes sense because you know there must be gas for these coronal lines to be emitted. But the other thing is that I've also looked at, I don't think I have it, do I? No, sorry, unfortunately not. I looked at their WISE emission and found, much like a lot of these other flares, again, that you have this transient infrared emission, which implies, right, that your ultraviolet flux is changing over time. So I should say, some of them are maybe AGNs. It's not clear that they're all TDs, but it seems that a large majority are TDs, and that potentially this is our only way to probe this extreme ultraviolet emission.
Thank you.
So you used this term black body radius. Could you explain a little bit what that means to the uninitiated?
Yeah, so for this, it's, a relatively simplistic picture, probably not extremely physically accurate, but we're just fitting their SEDs as a black body and effectively taking, the luminosity and the temperature and the Stefan-Boltzmann law and saying, so this is more of an effective radius, right? It's not, if it's a patchy photosphere or something like that, it could certainly be larger. But right, it's giving you, I guess, a minimum physical scale that you could have.
Okay, so you need enough spectral coverage to fit a good temperature for the spectrum, right?
Yeah, and so given the temperatures generally, Swift going out to a little bit blueward of 2,000 angstroms is pretty good. But yeah.
So I was curious about your thoughts on the coronal line emitters and the Mirongs, infrared flares, and the ambiguous nuclear transients.
Mm-hmm.
I think there's evidence that this is like a continuum of different manifestations of the same thing, or multiple classes. What is that?
I generally think, although I don't know that I have particularly strong evidence that it's some sort of continuum, that, especially in the infrared, the one nice thing about the infrared, right, is that it doesn't really care about what's happening. You simply know that you have a flare that's bright enough in the UV. And so that's why I think it's really interesting to follow them up in the multi-wavelength, and particularly the ants, and try to tease out, what are AGNs, what are TDEs. But I do think that there's some sort of continuum in terms of the properties, and right, you have a normal TD that's maybe in a post-starburst galaxy, you don't have any gas, and you just see these things, but as you add more gas, you have the coronal line emitters, but perhaps the dust distribution is patchy enough that you don't fully extinct all of the emission, but then as you have a higher coming fraction and more lines of sight are covered, then you lose your UV optical but still have the infrared. So I think it's probably a continuum, but I think it's worth us studying more and trying to understand if so, and where are the gaps and all of these different things.
For the types of the main sequence TDEs, are those spectra taken like at the same stage after the peak, or are they like different stages?
Yeah, that's a great question. These are generally near peak. I think we're doing better now selecting TDEs prior to peak, and so we can actually have a nice, time-resolved spectroscopy. Some of the earlier ones were not selected prior to peak, whether that's often it was seasonal breaks. You just had a source coming out of being too close to the sun. But the general point is true that the spectra of TDEs do evolve in some cases. You have different line species that are there early on and go away. You also have, of course, evolution and the line fluxes in widths. But yeah, the picture of the different spectroscopic classes is built on roughly near peak spectra. I should note that also, for TDEs as compared to, say, various classes of supernova, the spectra evolve somewhat more slowly. It's usually tens of days rather than, type 2 supernovae, for instance, right? You have day timescale evolution early on.
Yeah, I'm wondering whether for those like featureless could we see like the glow lines like appear again, or like whether the appearance of those brolines are related to the formation or the evolution of the broline region?
No, that's an excellent question. I think these TDE feature lists don't have, I forget off the top of my head exactly what their coverage looks like, but certainly, even if it's featureless near peak, you should still continue to look. And you bring up a good point about the formation of a broadline region and when does that happen. This is also maybe related to the question about TDEs and AGNs. Are you seeing the existing AGN broadline region get ionized? Is it the transient broadline region from the TDEs? And the final thing about the featureless TDEs I should mention is that it seems that they live in very different galaxies. They're more massive, have more massive black holes, and generally lower star formation rates. So there's some suggestion that perhaps these are jetted events and that we're seeing some sort of off-axis jet emission, although I don't know how much work in the radio has been done to kind of constrain that picture. But thanks.
Hi, thank you for the great talk. May I ask, could you comment more on the X-ray follow-up of the TDE? And also, because you said the TDE may be the origin of the coronal line event, and we know that we need high energy like soft X-ray to ionize those elements. So I was wondering, is the X-ray, the budget of the X-ray energy is enough to really produce this, luminosity of the lines?
So in terms of the X-ray follow-up, it's often with things like Swift XRT. And so, we mostly have constraints on the luminosity evolution. Some sources get things like Chandra, XMM, nicer follow-up. And so we have a little bit more on the spectral evolution. But I would say, at least the rate of X-ray TDEs from these optically selected are pretty good. Although sometimes TDEs only have a few UV X-ray points near peak, so it's possible we're missing some sort of late-time brightenings. But in terms of relating back to the lines, I don't know about trying to take some sort of model of how much X-ray emission you have to the line luminosities in particular. But I will say that the events that show helium emission are more likely to have X-ray emission than the ones that only show hydrogen. So it does seem consistent that if you have this soft X-ray emission that is enough to ionize these helium atoms, that it seems to be a consistent picture there.
So you're saying that you have seen the direct X-ray burst before the coronal line event or during the coronal line event?
Oh, sorry, you're asking about the coronal line, but I missed that. I don't know that our coverage is good enough in time to really. So oftentimes we take spectra of these and they already have the coronal lines, and then you have to go follow them up in the X-ray. So it's a bit hard for us to kind of say, how do they, is there a lag in time? Are they coincident? And it's only a few examples of ones that have been selected photometrically that show coronal lines. So I think we're only kind of scratching the surface of these types of events. And as with anything in this field, the difficulty is finding things early enough that you can get other multi-wavelength constraints, quickly enough to have really good, insightful information.